For centuries, people watched Jupiter's great red spot and assumed it would always be there, a storm bigger than Earth, apparently eternal, endlessly reassuring in its permanence. That assumption is wrong. The red spot is shrinking fast and its physics don't add up. It's not the only thing about Jupiter that stopped making sense. The deeper scientists look, the less this planet behaves the way it's supposed to. Here's what nobody tells you about Jupiter. It's actively rewriting its own rulebook, and nobody can explain why. A century ago, the Great Red Spot was massive enough to swallow 3 Earths side by side, stretching roughly 40,000 kilometers across. Today, it barely covers one Earth, down to about 16,500 kilometers. Since 2012, amateur and professional astronomers have watched it lose roughly 930 kilometers of width every single year. Hubble has been photographing this storm for 2 decades, and the trend line only points one way, down. Scientists used to assume the storm would simply stabilize once it shrank small enough for Jupiter's jet streams to lock it in place. That is not what's happening. Instead, the Great Red Spot is stretching taller as it shrinks, like clay being pulled upward on a potter's wheel. Basic physics says a spinning storm should spin faster as it contracts, the same way a figure skater speeds up by pulling in their arms. Jupiter's storm isn't doing that, it's breaking a rule that should be unbreakable. In 2024, Hubble caught something even stranger. The red spot doesn't shrink steadily, it pulses. Every 90 days it squeezes inward and stretches outward, speeding up and slowing down in a cycle nobody had ever documented before. Astronomers went looking for a hydrodynamic explanation for the oscillation. They found none. NASA researchers now say the next 5 to 10 years could bring rapid, visible changes to the storm's shape, possibly even a breakup. This is a weather system that has technically outlasted entire human civilizations, and it might not survive our lifetime, for reasons science genuinely cannot explain yet. If the one feature of Jupiter we can actually see through a telescope is behaving this unpredictably, what does that say about everything hidden beneath the clouds? For decades, scientists assumed Jupiter had a small, dense, rocky core buried at its center, like a cannonball wrapped in endless layers of gas. Then NASA's Juno spacecraft arrived in 2016 and began measuring Jupiter's gravity field with extraordinary precision, tracking tiny shifts in its own orbital speed to map what was hiding underneath. The core wasn't small, it wasn't solid, it wasn't even clearly separated from the hydrogen surrounding it. Heavy elements were smeared out across a vast region, gradually thinning into the surrounding gas like sugar, only half dissolved in water. Scientists coined a name for this mess, the fuzzy core, and fuzzy cores don't fit any planetary formation model anyone had built. For years, the leading explanation involved violence. A planetary embryo, roughly 10 times the mass of Earth, supposedly slammed head-on into a young solid Jupiter, smashing its core apart and forcefully mixing it into the metallic hydrogen ocean above. Simulations even matched the exact impact angle needed to produce the mess Juno detected. It was a satisfying story. One catastrophic collision explaining all of Jupiter's weirdness in a single violent afternoon 4.5 billion years ago. Then, in 2025, a new study published in the monthly notices of the Royal Astronomical Society tore that story apart. Researchers ran advanced supercomputer simulations and found the fuzzy core did not need a cataclysm at all. Jupiter could have built it gradually, absorbing heavy and light material simultaneously as it formed over millions of years. The planet's entire origin story just got rewritten, and scientists still do not fully agree on which version is closer to true. Even Jupiter's magnetic field refuses to behave predictably. It's the largest structure in the solar system, stretching millions of kilometres into space. And Juno found it's fundamentally lopsided, chaotic and messy across the northern hemisphere, calmer in the south, with an unexplained knot of intense magnetism near the equator that scientists nicknamed the Great Blue Spot. Then there's the lightning. On Earth, lightning requires liquid water colliding with ice deep inside storm clouds. Under specific temperature and pressure conditions, Juno spotted lightning flashing high in Jupiter's upper atmosphere, far above where that process should even be physically possible. By the rules we know, it shouldn't work. It does anyway. Nobody even knows what colour the Great Red Spot actually is, chemically speaking. Astronomers have tracked its size, its drift, its winds for nearly 2 centuries, and the exact compound responsible for that deep red-orange hue is still debated. Some models point to sulfur compounds dredged up from deeper layers, others to organic molecules altered by sunlight. In 2019, chunks of the storm began visibly flaking off its edge and dissolving into the surrounding clouds, fueling speculation the whole thing could disintegrate within decades. Other researchers push back, arguing the flaking might just reflect smaller storms getting absorbed and spat back out. Even the experts studying the same photographs can't agree on what they're watching happen. The magnetic field tells the same story of disagreement. When Juno first measured it directly, the field strength came in at 7.766 Gauss, dramatically stronger than models had predicted, and the variation across the planet was far more extreme than anyone expected. Some regions light up the instruments, others go strangely quiet. Scientists now think the dynamo generating all of this power isn't buried deep in the metallic hydrogen ocean as everyone assumed, but sitting in a shallower molecular hydrogen layer closer to the clouds than the models allowed for. That single revision reshaped how researchers think about magnetic fields on gas giants across the entire galaxy, not just this one. Studying any of this is brutal, which is part of why the mysteries persist. Jupiter's radiation belts are intense enough to kill an unprotected human in minutes. When the Galileo probe plunged into the atmosphere in 2003, it absorbed a radiation dose equivalent to 25 million dental X-rays before being crushed. Juno itself carries a 200 kilogram titanium vault just to keep its electronics alive during each close pass, and even then it can only survive brief windows near the planet before retreating. We're trying to solve a puzzle that actively fights back against the instruments sent to read it. Even Jupiter's moons keep the uncertainty going. Europa's subsurface ocean is one of the most promising places to search for life in the solar system, but Juno's gravity data still can't pin down exactly how thick its icy shell actually is, which matters enormously for whether anything below could ever be reached or detected. Ganymede is the only moon with its own magnetic field, and scientists are still working out how that field interacts with Jupiter's much larger one. Every flyby answers a question and opens 2 more. Put it all together and a pattern emerges. The storm we've watched for 2 centuries is shrinking in ways physics can't explain. The core we thought we understood turned out to be something scientists are still actively arguing about. The magnetic field breaks its own symmetry. The lightning ignores its own rulebook. Every mission we send to Jupiter tends to come back with fewer confirmed answers than it left with new questions. That's the real danger hiding inside this planet. Not that it's predictable and monstrous, but that the closer we look, the less we actually understand about what it's doing or what it might do next. Jupiter keeps rewriting its own rules. Subscribe, because whatever we learn next will rewrite them again.